So let's talk about something you experience every single day, but maybe don't give a second thought to. The feeling of hot and cold. It sounds so simple, right? But the science behind why some things feel instantly cold and others feel surprisingly warm? Well, that's a fascinating story about energy on the move. I mean, really think about it. You grab a metal doorknob and it feels cold. You get some laundry powder on your wet hands and it feels warm. They're both just sitting there at room temperature, so what gives? Turns out it's not really about the object's temperature at all. It's all about how it plays with the heat from your own body. And here are two perfect examples we see all the time. On the left, you've got that antiseptic hand gel that makes your skin feel so chilly. That's what we call an endothermic process. It's basically absorbing heat. And on the right, laundry powder feels warm when it gets a little damp. That's exothermic. It's releasing heat. This is the whole puzzle we're going to crack today. Why do these simple little changes involve gaining or losing heat energy?
All right, let's start by unpacking these everyday examples. We're looking for the one big clue that connects them both.
Okay, so this slide basically lays out the entire secret in two little words: absorbing and releasing. The hand gel feels cold because the alcohol in it needs a burst of energy to evaporate, to turn from a liquid into a gas. And where does it get that energy? It literally steals it as heat right from your skin. The laundry powder does the complete opposite. As it dissolves, it forms new, super stable bonds with the water, and creating those new bonds releases energy as heat, which makes your hands feel warm. So these two processes, absorbing and releasing heat, are a huge deal in chemistry. And of course, they have official scientific names. Let's get to know them. First up is endothermic. The trick is in the name. Endo means in or within, so an endothermic process pulls heat in from everything around it to fuel some kind of change. Our hand gel is the perfect example. Because it's absorbing your body heat to evaporate, the process is endothermic, and the result for you is that chilly feeling. And on the flip side, we have exothermic. Exo means out, so an exothermic process pushes or releases heat out into its surroundings. That's our laundry powder dissolving and getting all warm. So the easy way to remember this? Endo takes heat, exo makes heat. Simple as that. Now, this isn't just about weird chemicals. These two big principles are actually the engine behind the most common physical changes we see every day, the transformation of matter itself. And this diagram really paints the whole picture for us. See those arrows going up, from solid to liquid to gas? They need to gain thermal energy to make that happen. That's an endothermic process. And to go the other way, from a gas back down to a liquid and then a solid, it has to lose thermal energy. That's an exothermic process. Let's break that down just a little bit more. Okay, so let's look at the endothermic stuff, the processes that need to gain heat. Melting ice, evaporating water, even that cool trick where dry ice turns straight into a gas, all of these need an energy input. They have to absorb heat from their surroundings to happen. This is exactly why sweating cools you down. The sweat evaporates, and that's an endothermic process, pulling heat away from your body. And the opposite is true for the exothermic side. When water freezes into ice, or when steam condenses into water droplets on your mirror, they have to release all that extra energy they were holding. That release of heat actually warms up the surroundings. I know it sounds a little weird, but yeah, forming ice actually releases heat. Okay, so the theory is great, but how can we actually see this happen? Just by dissolving some simple powders in water? Well, let's look at a quick experiment. So here's the setup. We have two beakers of water, both sitting at a comfortable 25 degrees Celsius. In one, we're going to dissolve some sodium hydroxide. In the other, some ammonium nitrate. The only question is, what's going to happen to the temperature? And wow, check out these results. The sodium hydroxide made the water jump a whole 10 degrees, up to 35 Celsius, a textbook exothermic reaction. But look at the ammonium nitrate. It did the exact opposite. It dropped the temperature by 6 degrees, down to a chilly 19 Celsius. A perfect endothermic reaction, making the water colder just by dissolving a salt. And this isn't just about those two specific lab chemicals. Lots of common stuff has these properties. In fact, look at the list on the right. Sodium bicarbonate. That's just plain old baking soda. When you dissolve it in water, it actually makes the water just a tiny bit cooler. It's this fundamental property of chemistry, hiding in our kitchen cabinets.
All right, this is all really cool science, but let's get to the why does this matter part. Where do we actually use this stuff? Turns out the applications are everywhere, often hiding in plain sight. Let's start with maybe one of the most important inventions in your whole house. How does that big cold box in your kitchen actually do its job? Well, it is an absolute master of these endothermic and exothermic cycles. Your refrigerator is basically a heat thief. As this diagram shows, its job isn't to make cold, its job is to move heat from inside the box to outside in your kitchen. And it pulls off this magic trick by forcing a special liquid called a refrigerant to evaporate and condense over and over again. So it all boils down to this three-step dance. First, inside the fridge, that liquid refrigerant evaporates. That's our endothermic step, absorbing heat and making everything inside cold. Then, a compressor motor squeezes that gas, which makes it really hot. Finally, that hot gas runs through the coils on the back of your fridge and releases all its heat into your kitchen. That's the exothermic step, before starting the whole cycle over again. Okay, from the kitchen to the first aid kit, the exact same principles of releasing and absorbing heat are what give us those incredibly handy instant hot and cold packs. You've probably used these before, right? Inside the bag, there's a little pouch of water and some chemical powder. You just squeeze the pack, you break that inner pouch, the two mix together, and boom, you get an instant thermal reaction. No plugs, no microwave, just pure chemistry at work. And what's going on inside is exactly what we saw in those beakers. Instant hot packs use an exothermic reaction, dissolving a salt like magnesium sulfate to generate heat and soothe sore muscles. And instant cold packs, they use an endothermic reaction with, you guessed it, ammonium nitrate to absorb heat like crazy, getting icy cold to reduce swelling. It's brilliant, it's simple, and it works. So from the chill of hand sanitizer, to the constant hum of your refrigerator, to the instant relief from a cold pack, the science of endothermic and exothermic reactions is all around us. The real question is, now that you know what you're looking for, where else are you going to spot it?